Hello students, in this video we are going to understand about two important applications of op-amp. One is voltage follower and the other one is summing amplifier. First we shall discuss about voltage follower. You have learned how an op-amp is connected in a non-inverting mode. You give the signal here and you give no signal at the non-inverting terminal and you have these resistors. Now suppose if I want to change it as a voltage follower, what I basically do is I will remove the resistors R1 and RF from the circuit. Now we can see how the circuit will look like. This is how it looks like. You don't have any resistor R1 that is removed and you don't have the resistance RF, but instead the output voltage is directly connected to the input. Okay, and since there is direct connection between the inverting input and the output terminal, we can call this as a 100% voltage series feedback. Okay, this is the 100% voltage series feedback is taking place because no resistance is put, but directly the output is connected to the input. Okay, so this is the voltage follower circuit. You don't have any resistors R1 and R2, but it is connected in a non-inverting mode. Now how will you write the gain of the amplifier? You know that the gain of an inverting amplifier can be written as equal to 1 plus RF divided by R1, right? But then here you have this RF and R1 equal to 0. So then there is no this part. So I can say that the gain is here is equal to 1, which means that the amplification of the signal will not take place in this unity follower circuit or at a unity voltage follower circuit. Whatever is given at the input side is directly produced at the output side. No gain is actually happening, or you can say that the gain is 1. So you may be thinking why this effort is being utilized, because no gain is being or no improvement in the input signal is taking place in the voltage follower circuit. Then why do we connect it in this way? It has basically a main important application. It actually acts as a buffer. Buffer means it is actually a storing, you can call it as a storing device, or whatever is given in the input is directly given out. But then and that is what is normally called as a buffer. So now if this voltage follower circuit has a main implication in the major circuits, because you know that in major circuit normally you connect a big source. Okay, let me this be a source, and this source you may be connecting this source to the load, and this may be an amplifier which you are giving the source to the amplifier. Okay, so in this case what happens is that the source most of the time will be having quite a significant resistance, and if you are connecting a source the significant resistance to the amplifier, most of the time what happens is if the source resistance is high, the effective input resistance of the source, because the source is connected in parallel to the amplifier or into the load, we can call this amplifier or whatever you connect to the source as a load. So when the source is connected to the load, the effective impedance of this effective resistance of the source will actually get reduced, and because of the reduced load impedance when it is connected to reduced source impedance when it is connected to a load, actually this source will draw a large amount of current, and because of that very little voltage is actually supplied to the load. So that is actually a disadvantage when a high resistance source is connected to a load. Okay, so in that case if you connect an buffer amplifier here or a voltage gain amplifier in between, if you connect a voltage gain amplifier here, what happens? Let this be a voltage gain, or I can draw it. This is a source. Okay, and if you connect that source to a unity gain buffer or a voltage follower, let me call this as a voltage follower, and this when it is connected to a load, what happens is that because of the voltage follower's peculiarity, whatever is there in the source will be given directly to the load, because that is voltage follower, that whatever you give in the input you will get at the output also. So that will not hamper the source voltage. But now you know that this is an op amp, right? So this op amp basically has very high input impedance, right, input resistance, but the output resistance is very low. So output resistance is very low in the case of an op amp. So since voltage follower is very low, basically at this end, this end is what is being connected to the amplifier or any load. So what happens, effectively the source resistance seems to be reduced. So if the source resistance has a very low output resistance, actually this loading effect which I said earlier will not take place. That is actually a favorable condition. That is, a source having a very low resistance, internal resistance, is a favorable condition, that is actually a good thing to when you apply it to a load. So most of the sources will be having an internally a very high resistance. But in order to reduce that, if you connect that to a voltage follower, what happens is that voltage follower, because of the peculiarity of the op amp, reduces the output resistance at this side. So effectively the load sees actually a very low resistance offered from the source part. Okay, so in that way, this voltage follower has or do find application in various electronic circuits. Okay, so that is why we normally connect a voltage follower. One thing is that the output resistance of a voltage follower is very low, and a voltage follower doesn't hinders the source voltage. Whatever you give, that it will be given to the load. And because of that, this voltage follower is normally connected in many electronic circuits. And that is the application of voltage follower. Then another thing which you have to learn here is that about the common mode rejection ratio, CMRR. And common mode rejection ratio, you know that it is a differential mode gain divided by common mode gain. And then here this I can write it as closed loop gain. And differential, there you don't give any different signals at the input side, only the inverting voltage is only given at the inverting terminal. I call this as the closed loop gain divided by the common mode gain. Common mode gain is the gain which you get when you give the same signals at the inverting and a non-inverting terminal. Then this closed loop gain here, you know that is equal to 1 in the case of a voltage follower. So that 1 divided by common mode gain. So this is the common mode rejection ratio value of a voltage follower, that is 1 divided by common mode gain. Okay, that also you should learn. So this is all about the voltage follower, and now we are going to learn about the summing amplifier. Here I have shown the circuit diagram of a summing amplifier, and here an inverting amplifier is actually made as a summing amplifier. You can also use non-inverting amplifiers as summing amplifiers, but we are here we are only learning the inverting amplifier being made as a summing amplifier. Okay, so that means you actually keep the non-inverting terminal grounded, and at the inverting terminal you give the resistors. Okay, and you give the signal, and what it does is that you give many signals at the input. The output what you are going to get is actually the summed or total of the input voltages will be given or will be produced at the output, and that is why we call this as a summing amplifier. And we have to analyze the circuit and then understand how the summing action actually takes place. Now, as shown in your text, you can actually say that this is the voltage V1, or I can say you give a voltage here and connected to the ground, then you give voltage V2 here, so the ground. So say we can also draw in this way, no matter you do. Okay, so you have V1, V2, V3 given through the resistors R1, R2 and R3. Okay, so when you had only one voltage, you were connecting that using the resistance R1. Here you have, since three voltages, you connect each of the voltage through a resistance, which is termed as R1, R2 and R3 respectively. Okay, so now we have to calculate the output voltage VO. And you know that output voltage of an inverting amplifier, you have already derived it. What is that? This is actually minus RF by R1 into input voltage, right? That is how you studied. But you have here three input voltages, V1, V2 and V3, and you have only one RF, but then you have three R1s, and the place of R1 you have R1, R2 and R3. So what technique is basically used to find out the output voltage is basically a technique called superposition theorem, and which you will be learning later. But anyway, I'll just briefly tell you what it is. When you have many signals applied in this like this, we normally consider as, first you consider the one of the signal alone, keeping the other two thing grounded. So here we keep V1 connected to R1, but V2 and V3 we don't consider, as if it is nothing is given at V2 and V3, or we keep the terminal here grounded. R2 is grounded, R3 is grounded. So in that way, I can, when you analyze, then you next time when you consider V2, you consider V1 and V3 grounded. Next time when you consider V3, you keep V1 and V2 grounded. So, or I can say that you first will understand the result of the V1 alone at the VO. That is the first part. Then you keep forget about V1 and V3. Then you try to find what is the output voltage due to V2 alone. Okay. And the third time what you do is you forget about V1 and V2. See what is the resultant of V3 at the VO. Okay. So I am trying to do that. Considering V1 alone. Okay. So that means V2 and actually V3 is grounded. Okay, so considering the effect of V1 alone, then I can write VO as equal to minus RF divided by R1 into V1. Okay, this is the first time. Next, what you will do? Now you will keep you here actually V2 equal to V3 equal to 0, or it is grounded, right? Now what you do is keep along V2, V1 and V3 is equal to 0. Then I can write VO as equal to minus RF divided by R2. Okay. And the third time what you do is you keep V2 and V1 grounded. Then you find what is VO, that is minus RF by R3. Now what you do is, according to superposition theorem, you calculate the output voltages separately. Then what is the final voltage is basically, the final voltage is the effect of the voltage adding all these three together. So that is actually minus RF by R1 into V1, then minus RF by R2 into V2. That actually a plus sign is there, you add together, but you have this negative symbol here, that is why I put a negative here. Then, or I can say that plus this part plus the third part minus RF by R3 into V3. Okay. Now if you keep, so this is the actually the output voltage. Now if you keep this RF equal to, or next I'll show you. If you keep this R1 equal to R2 equal to R3 equal to RF equal to R, then what it is very easy, everything will get cancelled. Okay, so if it is then everything is equal, this will get cancelled, this will get cancelled, this will get cancelled, and then you will get the output voltage VO as equal to minus, negative sign is there, V1 plus V2 plus V3. So how does it look like now? The output voltage is actually the sum of all the input voltages. This is basically what is called as a summing amplifier. And you can think that why it is, since R1, R2, everything is put same, then only you can get this added effect, right? But otherwise also it is an adding amplifier added, or a summing amplifier, because only that each of the voltages, if RF by R1, RF by R2 and RF by R3 is three different values, then I can say each of the voltages weighted with a particular value and then it is added together. Or in that way I can also call this as a weighting amplifier, okay, where each of the weighted voltages of each input voltages is added together. So that is how a summing amplifier works. Or you can keep everything same and then show that VO is equal to the input output voltage is the added sum of all the input voltages. So this is another application of an inverting amplifier, and don't think that this only is a summing amplifier. You can also construct a non-inverting amplifier also in this style, or like circuit analysis may be slightly different, but then it can also be constructed as a summing amplifier. Okay, so in this video we were discussing about basically two applications of amplifier. One is a voltage follower or a buffer or a unity follower, in different ways you can call it, and the other one is a summing amplifier. Hope you understood these. If you have any queries, you can put it in the comment box. Thank you very much.